Thank you for having me today. I am Teresa Panurach. I'm a third-year PhD student at Michigan State University. Today I'm going to be talking about the work that I've been doing with my advisors Jay Strader and Laura Chomik, along with the Maverick collaboration on accretion jet coupling in luminous accreting neutron stars in galactic globular clusters. So I know we have an array of astronomers studying different fields of high energy phenomena here today. So to go back to what an overview of what exactly is a low mass X-ray binary. So they are binary systems that have either a stellar mass black hole or a neutron star accreting mass from a low mass stellar companion that's usually about a solar mass. So we're typically talking about K, M, or even white dwarfs. So those with a neutron star in the binary system are called neutron star X-ray binaries. And we should care about neutron star X-ray binaries and neutron stars in general because neutron stars are the endpoint in life for massive stars. And the more we study them, the more we know about the life and death of the star before them and their supernova mechanisms. And also, studying these stars, we get an idea of how a compact object turns accreted material into energy at different wavelengths. So here on the right, I show you a scheme of all the wavelengths you can use to study neutron star X-ray binaries. So for my presentation, I will be focusing on the X-ray, of course, and the radio wavelengths, which we use as proxy for accretion, so the inflow of material, and the jet, so how much material is being shot out. And so why study neutron stars in globular clusters? So on the right, we have a picture of one of my favorite globular clusters, 47 Tuc. And globular clusters have been known to contain large excesses of a variety of exotic objects like neutron stars and black holes. In fact, globular clusters are very enhanced with neutron stars and even form differently compared to the field. So these systems are usually formed dynamically. And so what happens is that these globular clusters are really old, dense group of stars, and the theoretical models show that denser, heavier objects like neutron stars and black hole sank towards the center and swapped with other objects in the cluster and created these systems in the first place. Also, neutron stars in globular clusters, we can get better luminosity measurements. So Milky Way globular clusters properties have been studied extensively, and we know a lot about their properties, including their distances. So since we know their distances, we can get accurate luminosity measurements compared to those neutron stars in the field, which is very important for the work that I do. And neutron star X-ray binaries have various accreting behaviors where they can turn on and off, and these systems are called transient systems. So in fact, most neutron star X-ray binaries are transient systems. So when the system is turned on, there is material being flowed in onto the disk. And then when the system is off, there's little to no material in the disk. And this is what we call the disinstability model. And so this explains the behavior of transiting neutron star X-ray binaries. So as I stated before, we use X-rays as a proxy to understand accretion behaviors. So in this plot here, we have a change of X-ray luminosity due to the mass accretion rate over time. And so what this model describes is what exactly is the thermal state of the gas in the disk? So is the gas in the disk hot or cold? And so when the disk is cold, we can assume that hydrogen is not being ionized and there's low accretion rate. So in this plot right here, this is where the lines are flat. So this is what we call the system is being in quiescence. But as time goes on, mass will eventually build up in the disk and it causes the temperature to rise. So after certain temperatures are reached, ionization happens, which in turn increases the mass flow through the disk to the compact object, which makes the disk hot. And then eventually the material will expel out of the disk, which we call the outburst state. So this is what you see in this peak right here. However, there are systems where accretion does not turn on and off, and these systems are called persistently accreting systems. And they persistently accrete material from 10 to the 34 to 10 to the 36 ergs per second in the X-ray. And these are the kinds of systems that we're going to be looking at today. So here on the right, I show you the radio X-ray correlation plane for accreting compact objects. So these include black holes, neutron stars, and also white dwarfs. So on the x-axis, we have X-ray luminosity that again we use as a proxy for accretion flow. And then the y-axis, we have radioluminosity that we use as a proxy for jets. And we use this correlation to kind of understand the coupling between the accretion disk and the jet. So on this plot here, we have the green circles represent black holes, while the other symbols represent the diversity of neutron stars, and including other accreting compact objects like CVs that are white dwarfs. And so we study neutron star X-ray binaries because unlike black hole X-ray binaries, little study has been done to understand the radio emission from quiescent hard state neutron star systems, especially those that are persistently accreting. And also, we used to believe we can tell what was a neutron star and a black hole just by looking at both the radio and X-ray wavelengths. Black holes tend to be more radio loud than neutron stars. So as you can see right here, the black holes are right here. But the more we observe these different types of systems, the more they start to overlap, which you can see right over here, especially in that range. So another question we want to ask is, can we really tell what's a neutron star and black hole just by looking at the radio and X-ray? And lastly, for some time now, we deduced that there is some agreeable correlation for black holes, again, those in the green circles. There is some scatter, but they mostly follow this gray dash line that you see right here. There is some scatter. However, with neutron stars, it's a little bit more complicated. The slope of the line can vary just by what data you're looking at. And unlike black holes, neutron stars seem to be all over the place. And so another thing we want to know is that, do neutron stars follow a track like black holes? So in my project, we are doing a systematic radio and X-ray study of the largest sample of persistently accreting neutron star X-ray binaries, along with 2 other transient sources that we had in our survey. And we use nearly simultaneous radio and X-ray observations for each of our systems, which is very important because neutron star systems, they tend to evolve very quickly. And so the data that we are using is our collaborations radio survey called the MAVERIC survey, which uses the VLA and ATCA. The MAVERIC survey consists of observing a sample of 50 nearby globular clusters to look at radio candidates showing signs of accretion. The original intention of MAVERIC was based on the idea that neutron stars and black holes could be separated, but as I said before, this has become less clear over time. And for our X-ray observations, we use mostly Swift and Chandra. And so like I said before, it's very important for us to get strictly or quasi-simultaneous, so a day or 2 apart in the observations, because we want to know what exactly is going on between the jet and accretion disk at the same moment, since neutron stars evolve so quickly. So in our results, we show the radio and X-ray correlation plane on the right with all of our sources, which are the large colored X's that you see here. And those with multiple X's with the same color are the same source, but we just happen to have multi observations for. And so the green circles, again, are the black holes, and the other icons are the other kinds of neutron star systems. So plotting these systems, we do show that neutron stars do not follow a single relation compared to the tight correlation that we see in black hole X-ray binaries. Now that we added the critters that I've studied, the population of neutron stars are definitely more scattered than before. However, we do find some new information about neutron star X-ray binaries, which is kind of exciting, is that some of these systems that I will go into further detail later, they can be as radio bright as the black holes at the same X-ray luminosity. And then another source in particular showed dramatic radio variability. And so first, we're going to take a look at this source. These are the black X's, and this is GRS 1743312 in Teresa 6. So this source is one of the transients that we caught in our survey, and this shows regular outbursts about every 6 months. And we were fortunate enough to have 3 quasi-simultaneous observations that showed different behaviors at every observation. So we had one observation right here in the middle that showed that the radio, it was completely non-detected, which you can see in this downward arrow that represents a radio upper limit. But then a month later, it showed one of the most important things about this system, which is directly by the black hole population. So this means that neutron stars can be as radio bright as black holes. And this is exciting because one of the ways we could differentiate between black holes and neutron stars is that black holes tend to be more radio loud. So however, we do see that now neutron stars can indeed peak up into that black hole population. So radio loud things can be either black holes or neutron stars. And here is another one of our little critters. This is X1850087 in the globular cluster NGC 6712, and this is one of our persistent sources. So this particular critter was undetected in our initial Maverick observations in the radio. However, in the later observations, we saw that the radio jet turned back on, so it was detected again in the radio. So we decided to delve deeper into both past and present X-ray and radio data to see what exactly is going on with this source. So this plot is a little all over the place, so I'm going to try my best to explain it the best way that I can. So this plot shows both radio and X-ray light curves for X1850. So the top half of the plot shows X-ray light curves from Ginga, RXTE, and MAXI, while the bottom half shows archival data from our Maverick observations, as well as archival data from the VLA. So the solid red lines in the X-ray plot signifies when it was detected in the radio, while the dotted lines represents non-detection, as you can see right here. So the X-ray light curve shows fairly typical behaviors with regular outbursts that you can see in these peaks right here. However, it doesn't really help us explain the dramatic radio variability that we see here in our later observations with Maverick. The jet was on for a bit and then it turned off and then it went on again. So unfortunately, there is no swift XRT coverage for these observations. So that's why we used MAXI light curves. But the MAXI light curves do show that there is some sort of outburst during this time, which is shown in this little peak right here. And then it transitioned to a softer state. So this could be the reason for the variability. However, I feel like this is a rather oversimplified explanation. So the source was detected for a few days, and then it went completely off, and then it went back on in such a short amount of time. This would require like different separate transitions between the fainter, harder, and the softer state that doesn't really show in the light curves that much. Overall, we concluded that this is the reason why that this is like that explains the dramatic radio variability, but we don't want to confirmly like rule this out without getting additional radio and X-ray observations in the future. So in summary, we know that neutron stars are important for relativistic jet launching and their mechanisms as well. And the big takeaway that I want everybody to get out of this presentation is that neutron stars do have a broader radio luminosity range than previously observed before. And now that we know this, there's like really exciting ways that we can move forward is that after delving into the higher luminosity end of neutron stars, something we want to do in the future is looking at the quiescent critters to see where exactly they reside on the radio and X-ray correlation plane. And also, I mentioned this a little earlier, the second thing that we want to do is do some radio and X-ray follow-up on X1850 to really understand what's going on with this source and whether or not the detection and non-detection in the radio is simply due to X-ray transitions or something more complex is actually happening. Okay, thank you so much for listening.
Great, thank you very much.
Yeah.
We have a few questions submitted here already. This one is from Chris Brazil, who asks, how do you know that GRS 1743 is a neutron star system and not a black hole?
Yeah, so the typical way that people differentiate between neutron stars and black holes is if they have type 1 X-ray bursts or there's like some pulsations. I'm guessing because black holes don't have a surface that they can really do that.
Great.
Mm-hmm.
And just as a follow-up to that, is there sufficient coverage on all of these sources to feel like if there were type 1 X-ray bursts, you would have detected them? Or in this case, I guess you are detecting type 1 bursts because they are.
Yeah, like the reason why we chose these sources in particular, because we definitely knew that these critters were neutron stars.
Right, got it.
Excellent.
Yeah. So the next question is related to the link between black holes and neutron stars. This is from Krista Smith, who says, you may be aware of the black hole fundamental plane, which relates the radio luminosity, X-ray luminosity, and black hole mass in a type 3D correlation. Mm-hmm. I suppose it doesn't make sense to add neutron star masses into your analysis here because they all have similar masses, but is there such a plane for neutron stars as well?
I guess like the black hole and neutron star comparison, this is also like it has black holes. So I guess like people like to compare both black holes and neutron stars. So I don't know, the more people add neutron star systems to this correlation plane, the more I see that there's just no correlation like there is for black holes. They just seem to be super scattered and all over the place.
Great. And presumably, again, as she mentioned, because these all have the same masses, there isn't an additional axis that you could find that would tighten things up in the way that they did with.
Yeah, I think this correlation is just solely based on like the luminosity and not really the mass.
Okay.
Yeah.
So Pranav Ghosh has a question. The same Maverick data has shown the absence of intermediate mass black holes in globular clusters with implications for the formation scenarios. And in terms of the accretion relationship shown here, the radio X-ray correlation implies a more complex interaction between accretion and jet dynamics in neutron stars than in black holes. And so what extra parameters other than accretion rate do you think might be relevant for understanding this complexity? You got into this a little bit in talking about the variability, but I'm curious if you have any more thoughts on that.
Yeah, that is definitely something that we may want to go further into in the future. Yeah, that's a good question. Thank you.
Great. And then last question is from Brian Greffenstedt, who asks, apologies if he missed it, but are these targets known Z-track or ATOL sources?
I know some of them are ATOL sources, yes. Mm-hmm. Yes, and also some Z sources, yes.
Right. Which is further evidence that they're neutron stars.
Yeah. Okay. All of them are for sure neutron stars. Do not worry, everybody.